All right, we are at the top of the hour, so I am going to get us started. Hello, everybody. Welcome to today's live broadcast. During this webinar, we'll explore advances in thermal desorption for environmental contaminant analysis. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. A quick note about quantum analytics. We are a value-added turnkey solutions provider offering an array of customized instrument financing solutions combined with technical services, installation, training, and product support. Quantum Analytics is proud to be a service and sales provider for Marks International thermal desorption products, and we are very excited to spotlight these solutions during today's session. Which brings me to our webinar presenter, Hannah Calder. Hannah is a specialist in the use of pre-concentration techniques for environmental air monitoring and has been a member of Marks International's global team of technical experts for 7 years. Specializing in thermal desorption, Hannah sits on international standards committees as a technical advisor and has extensive practical experience using TD as an analytical tool for a wide range of applications. Hannah's analytical chemistry experience also extends to mass spectrometry and advanced separations, with a particular focus on two-dimensional gas chromatography with time-of-flight mass spectrometry. As a registered guest, you'll receive a link to this recorded webinar in your email when it becomes available. The webinar, including Q&A, will last about 45 minutes. Type your questions at any time into the text box in the question module that you see at the right side of the screen, and Hannah will answer those at the end of the webinar. Well, this ends our introduction, so without further delay, I present to you Hannah Calder.
Thanks very much, Lauren. So as Lauren's just outlined, in this presentation today, we're going to be looking at how thermal desorption combined with GCMS is able to respond to the changing demands of regulated monitoring in air, and how thermal desorption is being used in cutting-edge research to aid the understanding of these emerging compounds and look at their effects on human health. I'll be showing short application overviews today and hope to showcase the versatility of the instrumentation for environmental monitoring. So since the 1960s, there's been a growing concern about harmful exposure to low levels of hazardous pollutants. Now, these concerns have led to tougher volatile organic, or VOC, monitoring programs worldwide. And that's resulted in a number of challenges for analysts. Analysts are now being asked to negotiate challenges such as increased monitoring frequency, larger lists of target compounds, and to reach even lower detection limits. A recent example that we're going to be talking about today is the update to US EPA method TO15. And on top of that, air research continues to identify new and challenging compounds to monitor, such as PFAS, microplastics, and particulate matter, which dominate the global environmental news today. Now, for anyone joining us today who's new to air monitoring, we're going to have a quick look at what the challenges are when we're trying to measure VOCs in air. Now, VOCs are harmful at very low levels, so analysis is not always straightforward. To give you a quick example, the World Health Organization guideline for benzene in air states that there is no safe level of exposure, and even concentrations as low as 0.05 ppb is associated with an increased risk of leukemia. If 1 ppb is roughly a drop of water in an Olympic-sized swimming pool, and this is 50 times lower, then that gives you an idea of the scale that we're looking at here and what the technology needs to be able to do in terms of getting down to these levels. And the solution here is pre-concentration with thermal desorption. So how does pre-concentration work with TD? Well, the simplest form of thermal desorption is to use sorbent tubes. Now, these sorbent tubes can be packed with multiple absorbent materials to collect a broad range of analytes. Now, these can be very volatile compounds, which we can collect on our strong sorbents, or semi-volatile compounds which get collected on our weak sorbents. The air is pumped onto the sorbent bed, traveling through from weak to strong, and the compounds of interest are adsorbed onto the sorbent's surface, allowing lighter gases that we don't want, such as nitrogen and CO2, to pass through. Once we've taken the sample, the tube is then taken back to the lab for analysis. And in the lab, the tube is heated and carrier gas sweeps the compounds off in the opposite direction to which they were sampled. This technique, where we reverse the flow, is called backflushing, and it's the reason that we can use multiple solvents to collect a wide range of compounds using this technique. So if we have a look at the range of compounds that sorbent tubes can capture, we can see from this diagram that from C3 all the way up to C44, sorbent tubes are able to collect these compounds. But sorbent tubes aren't the only way of approaching thermal desorption. You can also collect your samples in canisters, which are really one of the main ways of collecting samples in the US today. And you can also take online measurements. Now, canisters and online have the advantage of being able to capture whole air. So they can look at very volatile compounds, such as the C2s, ethane, ethene, and acetylene that we can see here, which sorbent tubes just can't do. This gives them advantages in certain situations. For the majority of samples, though, any of these techniques can be suitable. So once we've got our tube back to the lab and we've put it into the instrument, our sample is transferred from the tube in the carrier gas and then refocused again on an electrically cooled trap within the system. Now, this electrically cooled trap also has multiple sorbents within it. So again, we can capture a really wide range of compounds onto this trap. At this stage as well, we've got an optional split. So if we have high concentration samples, we can split some of that sample away. In the MARC system, it's possible at this point to recollect that split flow for reanalysis at a later date. With thermal desorption, though, as we just discussed, tubes aren't the only way of introducing the sample. So if we've got online samples, canisters, or bags, we introduce that whole air directly onto that multi-bed focusing trap ready for analysis. Now, step 2 of this pre-concentration effect is the desorption of the trap. Now, once our compounds are on the trap, we then need to heat them up again to release them into the flow of carrier gas. And again, we're doing this in backflush. So we're releasing the compounds off and they're going into the GC. Now, this is a really quick operation. So the analytes are transferred in a really small band of gas, and this gives us great sensitivity because we get really good peak shape, even for the very volatile compounds. Now, at this stage again, we can also have an optional outlet split. Now, the split flows can be recollected again for reanalysis at a later date. Now, in many applications, tubes or canisters will be suitable, and each gives a significant amount of pre-concentration. So if we look at an online air sample, we've got hundreds of milliliters that are going to this focusing trap here. For canisters, we can take liters from the air and then transfer hundreds of milliliters onto the focusing trap and then hundreds of microliters into the GC. So at each stage here, we're pre-concentrating and reducing the amount of gas that we're injecting, but keeping the compounds the same. Now, for solvent tube sampling, we have the ability to take hundreds of litres of sample in certain situations. So this is then transferred in hundreds of millilitres of gas to the focusing trap, and then hundreds of microlitres of gas to the GC. Again, at every stage, the amount of gas gets smaller, but the amount of compounds we have remains the same. So we're pre-concentrating at every step. And for solvent tubes, the overall concentration factor can be up to 10 to the 6. So when we're dealing with these really low levels of harmful compounds, TD has the ability to really look and see them. Okay, now I can't begin a talk on air quality measurements without spending at least a little time on the TO15 update. Now, for those of you who are listening today that aren't monitoring air toxic compounds, I'm going to briefly review what TO15 is before we begin to look at the update and what changes have been made in TO15A. So what are air toxics? Well, air toxics are any volatile organic chemical which causes harm to human health and the environment. Now, the EPA listed about 90 compounds, excluding some of the non-methane hydrocarbons, which were already monitored separately as part of the PAMS method. And these compounds range from very volatile species like propene down to the heavier volatiles like naphthalene, but they also include halogenated and polar species like the vinyl chloride and ethanol you can see here. So it's a broad range of different species and a wide range of volatility here. Now, these compounds are monitored at concentrations ranging from high ppb all the way down to low ppt. And the sampling analysis is carried out using one of two EPA methods, either TO15 for canister analysis or TO17 for tube analysis. And it's TO15 and canister analysis we're talking about today. Now, most labs doing TO15 will be doing a subset of either the 65 compounds that are commonly looked at or less. Now, these compounds can be sampled from various different locations. It can be rural, semi-urban and urban locations, as well as industrial and agricultural sites. And it could also be indoors to assess the air quality we're being exposed to in our homes. Now, in TO15, the method detection limits here were 0.5 ppbV. And with that, we can do enrichment from up to a litre of sample. Now, the technology used is TD with a multi-solvent trap with separation using GC and MS detection. Now, TO15A was released in March this year, and it was released by the EPA 20 years after the original TO15 method. TO15 has become one of the go-to methods worldwide for VOC analysis using canisters, and updates to TO15 were first mentioned in 2016 when the comments process started. So we've been expecting this for a while. So what has actually changed? Now, on the face of it, the first thing that a lot of people will notice is the method is much more in depth. It's a great resource for anyone just starting out in canister analysis, and this was part of what the EPA were trying to do when they wrote it. It's very thorough in its instructions on parts of sampling and analysis, and they also wanted to give users and people carrying out the method the confidence to troubleshoot this analysis as well. Now, there's two big changes we're going to talk about today, and the first is the one that will affect a lot of people, and that's the fact that the method detection limits have dropped to the range of 20 pptV. So if you remember in the TO15 summary we just looked at, previously that was 0.5 ppb. So this is a big difference. And also, another change is the fact that water management techniques are now included. In the previous method, there was no guidance on how water should be managed other than dry purging the trap prior to injection. So, the choice by the EPA to drop the method detection limit so significantly is due to a number of factors. And the more positive one is that the air quality has improved massively over 20 years. These toxic compounds are now present at much lower levels than they were. And the other factor is that technological improvements in terms of the canisters, the TD instrumentation, MS instrumentation, and also the advances in water management have enabled labs to now get down to these levels. But what does the drop in MDLs actually affect? There's a few things that we're going to need to think about going forward. The first one of these is sample volume. So as the levels have dropped, it's now going to be important to have a bit more flexibility to take larger volumes of sample. Instruments and potentially even canisters, which aren't able to take a litre of sample, may struggle to reach the MDLs. And in these cases, you do want to be able to have the flexibility to take more sample if you need to. Another consideration is actually the process of pressurizing canisters prior to analysis. This effectively dilutes the sample and will add extra analytical strain. Certainly, taking larger volumes again, if we're pressurizing the canisters, will become very important. The next consideration is detector technology. Now, a lot of older MS instruments currently being used may not be able to get down to these levels. SIM is an option, so that's definitely a starting point for a lot of labs, but investments in newer kit may be necessary. But modern quadrupoles are able to get down to these levels. And alongside the quadrupoles and ion traps that were previously specified in the method, time-of-flight technology is now also a suggested detector type. And finally, there's cleanliness. Now, because the method detection limit has changed, obviously the specification for the instrumentation, the canisters, now needs to be much lower as well, 20 pptV or below. And this is the biggest challenge the EPA saw, not so much from the instrumentation side, but the process surrounding canister cleaning. Anyone who's worked with canisters will know that sometimes you just can't get them clean. And sometimes it can be a longer process to achieve the levels that you're looking for, especially when they've come into contact with a high concentration sample. Now, in terms of the instrumentation, if we do come into contact with a suspected high-level sample, it is possible to screen canisters using loop sampling, where you inject a very small amount of that sample into the instrument, so you don't risk overloading the analytical system, be it the GC column, the MS, or even the TD. So there's things we can do there. In terms of the next thing, which is water management techniques, the requirement and range of compounds for TO15A means that some traditional water management techniques like membrane dryers are not suitable for this analysis. They remove polar compounds and oxygenated compounds from the sample. And what is recommended and used by the EPA is devices like the Cori XR that you can see here. Now, efficient water removal from the sample is achieved by freezing the water at -30 as it passes through the Cori. So if we can see on the schematic, the air, standard or blank, all travel through the Cori. The water is then frozen at this stage, and our VOCs then pass onto the focusing trap as normal. Now, this process happens, and we don't lose any of the polar or oxygenated compounds we need to retain in this sample. But why have they included water management now, and what does it actually do to help us? Um, Water management can help in a number of different ways. The first way is it can really help us to lower the detection limits. So in the previous slides, we saw that taking larger sample sizes may be something that labs have to consider now. And if you're taking a larger sample volume, you now need to be a bit more concerned about your water as well. More sample definitely means more water. So removing that water removes an interference at that stage. So that means we can reach lower detection limits with larger sample volumes without a lot of hassle. It also massively increases our confidence in results. So on the side of the page here, you can see a chromatogram, 38 overlaid chromatograms, which were taken over the period of a month by the New York State Department of Environmental Conservation, using a CA Advantage and a Cori. Pete Fedina from New York State, who ran these samples, said he'd never seen retention time stability like this until he used the Cori for his samples. And this stable retention time can really help with compound identification. If you run your standard and the compounds are coming out at the same time, you've got a good shot at getting that identification right. It also reduces other water interferences as well. And less water on the column means less instrument downtime. Water does, as it's introduced to the column, begin to strip away the column phase. So by introducing less water to the column, we massively extend column lifetimes. And because that phase that's being stripped from the column isn't then entering the MS, we don't have to spend as much time cleaning our MS source either. So it's got a double benefit there. Now the Marks TO15A solution is the CI Advantage XR with Cori XR for removal. And what this system gives you is excellent peak shape, excellent productivity. The profile here shows excellent transfer for the system. We've got really good transfer of those heavier compounds in the sample, which is important to look for. Great peak shape, even for the very light compounds like propene and vinyl chloride. And for oxygenated compounds like the isopropanol. It's also a fast turnaround, so all the compounds here have been analysed in under 25 minutes. We can also show linearity up to a litre of sample for all the compounds in the TO15 mix, and MDLs well below that required by the TO15A method. So what are the benefits of this Mark solution, apart from the technology ones you've just seen? Well, for a start, it's cryogen free. So this can save thousands of dollars per year. And when we don't have cryogen, we also gain a bit of peace of mind. Systems which are cryogen free can safely operate for extended periods of time without the need for any manual intervention and without the risk of cryogen running out or not being available. The system's upgradable with Cori XR from water management anytime. So anyone who has a CA Advantage can add Cori XR to their system. And this, as we've seen, allows you to lower your detection limits, increase your confidence in results, and decrease your instrument downtime. Now, the ability to take samples from unpressurized canisters is something that a number of our customers find really useful with the CIA. It can halve your sample prep time. It avoids the need for sample dilution, which when the method detection limits have dropped so much is really key. And again, it can increase confidence in results because you're removing a manual step in the process for your analysis. It's one less thing to go wrong. And of course, we can take up to a litre of sample. So if you do need to stretch and take as much sample as possible, you can definitely do it with this system. Another benefit is the ability to do TO17 and TO15A on a single system as well. So the MARC systems can be configured with an Ultra XR for tube sampling, and both of these systems can run on a single GCMS with no manual intervention needed from the user. So if your customers are considering using TO17, or you have another set of customers considering looking at TO15A for their analysis, this system is able to do both without any extra expenditure on the GCMS as well. But TO15A is just one of the new challenges in air pollution monitoring. Another one that we're going to talk about today does involve air toxics as well, but it also involves ozone precursors, which are the smog-forming compounds, usually very volatile non-polar hydrocarbons, as measured in the US EPA PAMS network, and oxygenated VOCs, such as aldehydes and ketones. And a compound of real interest here is formaldehyde. Formaldehyde is of interest for both human health and environmental reasons. It's a chemical of concern for human health because it's of high toxicity and it's a probable carcinogen. Environmentally, it can break down to form formic acid in the atmosphere and carbon monoxide, as well as acting to create ground level ozone upon reaction with NOx. Now, what's being approached at the moment is combining these three lists for a total of 117 compounds measured in a single analysis in 1 hour. Now, this is a method that's soon to be mandatory in China, but it's of growing interest worldwide as labs try to expand what they can achieve in a single analysis. And again, of specific interest is the integration of formaldehyde here. This is one of the only methods where you can analyze formaldehyde alongside other VOCs without any need for derivatization. Traditionally, formaldehyde is monitored using DMPH cartridge and then HPLC. So anyone who's looking to do formaldehyde and VOC monitoring has to run two completely separate analyses. Now, it's a really wide compound range that we're looking at here. So there are a number of challenges we need to address to be able to get this successful analysis. And the first one is the fact that we need to be able to trap the full compound list and get good desorption of all these compounds as well, as those sharp peaks will aid our GC separation. It's also important that this system can run automated, unattended analysis. You don't want to have user intervention at every step of the way. And if we're going to have an unattended analysis, independent system performance checks with the addition of an internal standard is important as well. Now, as we've seen, if we're going to look at polar compounds, we need a water management technique that doesn't remove them. And water management is important because large sample volumes will give us maximum sensitivity for this analysis, as with TO15A. As well, it protects the GC column and detects us from wear due to water. Now, key for formaldehyde is the ability to sample from canisters and online in the same bit of instrumentation. Now, in the Chinese method, there's a lot of discussion currently about whether formaldehyde will actually be included as part of the list, and that's the main reason it's not been released yet, apart from the global pandemic as well. So formaldehyde in canisters is stable for a certain amount of time, but there are questions about how long that time is and if it's practical for labs to really monitor formaldehyde from canisters. So being able to do an online sample directly from the air into the instrument gives people another option for formaldehyde. And of course, we need to achieve all of this with a cycle time less than 60 minutes. it's really important in specific air monitoring applications that you get good time resolution. So you can have a data point every hour and see the changes in the VOCs as the day progresses. And we need to do all of this without liquid cryogen for either the trapping or the chromatography. So the system that's going to be able to do this is again the CA Advantage with the Cori XR. And you can see from the schematic here that the CA Advantage is capable of taking that online air stream as well as being able to analyze up to 27 canisters. As the sample passes through the system, we can also add internal standard and sample via an MFC or a loop. Once we get to Cori, the water is then removed, again by freezing, and the samples transferred to the focusing trap, ready for injection into the GC. Now, as part of the TD stage, there are 3 fully automated stages of operation. The first one being the sampling. So the humidity is removed using the Cori trap, and the target compounds are collected onto our electrically cooled focusing trap within the system. Step 2 is the trap purge. Now, there might be some residual water that's come through with the compounds of interest. So at this stage, we can remove that by performing a dry purge of the focusing trap before the analysis. And then finally, we have desorption into the GC. Now, the focusing trap is rapidly heated in backflush to inject the analytes onto the GC column. Simultaneously to this, the water from the Cori trap is removed by heating up the Cori as well. And this water is then sent to vent, so it's ready for the next sample. So that's it for the TD system. But what's happening inside the GC? Now, this is a very big compound list. So we need to use a Dean switch to make sure we're getting the best chromatography for all of the compounds on that list. Now, Dean switches are used commonly in the ozone precursor analysis. So this is fairly common for looking at these specific compounds. And the compounds we're looking at here are the C2s and the C3s. So we have our sample, which is introduced to the primary column. This, at this stage, follows the red arrow and is diverted to a secondary column for detection by FID. This secondary column is what gives us the separation, so the baseline resolution that you can see here for the C2s and the C3 compounds. And it's also what gives us some of the excellent peak shape. Now, the second stage is to introduce the sample straight down the primary column, following that blue arrow, and then going to the MS via a piece of fused silica. Now at the MS, we then have the other 112 compounds for separation. And the separation and peak shape here are really important. So we can see formaldehyde, great peak shape. It's highly reactive, so this is really important for the analysis. Polar compounds such as acrolein have good peak shape as well, and then semi-volatile compounds such as naphthalene also with good peak shape here. So we can say at this stage that we've managed to trap and separate those 117 compounds. And we can do it quantitatively because we've got excellent linearity even when the standard is introduced at 100% relative humidity. The standard you can see here was introduced at different volumes. So we've taken from 50 to 600 ml from the same canister. And that's equivalent to about 1.25 all the way up to 15 ppb. All the air squared values here are at least 0.99, and we've got relative response factors which are highly reproducible as well. Next thing to look at is the method detection limits. So all of the method detection limits here were below 200 ppt. The aim for this analysis was to have 500 ppt, so we're well within what was required. And actually, apart from a few outliers, the average method detection limit here is 50 ppt. So that's actually really close to what TO15A is asking for. So with this system, we managed to tick all the boxes. We've got a cryogen-free quantitative analysis from the very volatile up to the semi-volatile organics in this sample. We've got quantitative analysis of formaldehyde by TDGCMS. It's completely automated and can be set up for unattended analysis. The water management is successfully removing water without losing those polar compounds. And we have the ability to sample from canister and online. All in all, we managed to get separation of those 117 compounds within the 60-minute cycle time as well. Now, it's worth saying at this point that many labs outside China aren't trying to replicate this analysis exactly, but rather it's inspiring them to look at what is possible with the systems they have. As we discussed at the beginning of the presentation, monitoring programs aren't getting any easier, and having the ability to push your system to do more is a great advantage, especially given the competitive nature of the monitoring market today. So now we're going to move from VVOCs all the way down to SVOCs, and we're going to have a look at airborne particulate matter analysis by thermal desorption GCMS. So airborne particulate matter is made up of a collection of solid and or liquid materials of various sizes. So you've got PM2.5 and PM10. PM2.5 is the fine particles. These have a diameter of less than 2.5 microns. And then PM10 is your coarse particles like dust and pollen. And these have a diameter of less than 10 microns. Now, PM is made up of materials which are either directly emitted into the air or result from the transformation of gaseous pollutants. And what's important is where these pollutants come from. And there are various different sources for particulate matter. It can be industry, vehicle emissions, or natural sources like forest fires and volcanoes. Now, people are exposed to particulate matter pollution when they breathe. And the reason that particulate matter monitoring is so important is because it can cause severe health effects. It's estimated there's 4.2 million deaths every year as a result to ambient air pollution. And 91% of the world's population live in places where the air quality exceeds the World Health Organization guideline limits. So finding the sources, understanding where this pollution is coming from is really important so that governments and industry can strive to reduce it and improve air quality for everyone. Now, currently, PM2.5 analysis is generally carried out by sampling the PM2.5 onto a quartz filter using an in situ sampler like the one you can see here. This filter is then taken back to the lab and it's either punched or cut up into sections. Now, these sections are then solvent extracted with sonication. And finally, after they've gone through the solvent extraction stage, the solvent is blown down with nitrogen to concentrate up the compounds in the solvent. Now, this is quite a manual process. It's also very time consuming and costly because you have to use a lot of solvent and you have to therefore dispose of a lot of solvent waste. And on top of that, the multiple handling steps can lead to errors. Now, with thermal desorption, this process is massively simplified. So we take the filter, it's sampled in exactly the same way, but you can either punch holes out of it as shown here, or roll the filter up and place it inside an empty TD tube for direct desorption. Now, once it's in the tube, the system does the rest and you have separation and identification by GC-MSD. Now, there's minimal sample prep here compared to the previous method, and therefore it's much quicker, and there's no solvents required, which makes it much cheaper as well. And we get results such as those you would expect from a PM analysis. Now, the chromatogram here, we're able to pick out key compounds such as these PAHs. And being able to detect these compounds here shows the suitability of the system for these SVOC compounds. Now, this is a massively simplified sample prep process, saving labs time through less manual handling, as well as increasing confidence in results. And as I've said several times, it saves money because it's a solventless technique. There is more and more focus globally on green solutions, and getting rid of solvent is one of the ways to achieve that. So we're also going to touch on microplastics analysis today, and the example I have here is microplastics in water. Now, microplastics is an emerging global problem. They're found in our environment from a wide range of sources, and the buildup of toxic chemicals due to their degradation is really harmful to aquatic environments. The bioaccumulate and leach persistent organic pollutants as well, including endocrine disruptors. Now, a microplastic is commonly defined as a particle with a diameter of less than 5 millimeters, and it can be extracted from water samples using filtration. Now, there is a variety of analytical techniques under investigation at the moment, and one of them is thermal desorption. So the process for taking a sample here is we take hundreds of mils to liters of water, and those are passed through a filter. This filter is then washed with multiple reagents to remove the organic matter, and then dried. This dried filter can then be placed directly into a thermal desorption tube for analysis. So again, minimal sample prep here. So we've been working in collaboration with Eurofins Aproma to assess this technique for microplastic analysis. And the starting point was to look at polyethylene terephthalate, more commonly shortened to PET, in bottled beverages. Now, there are big concerns with PET leaching into drinks from the bottles. So what Eurofins have done is they've identified marker compounds for the PET, which they've identified by placing standards of PET pellets into the direct desorption tube and then heating them with the thermal desorber. Now, what they found is that you can use 2,4-ditertiary butyl phenol as a quantitation marker, which will tell you how much PET is in your sample. And then you can use tetrahydrofuran and acetaldehyde to confirm the presence of the PET as well. So the bottled beverage samples were filtered and washed, and then the filtrate was analysed by TDGCMS. Now, the first step was to use a spiked sample. So PET was put into water, filtered, and went through the entire process. And this showed better than 90% recovery for the PET from the filter. And we can clearly see here our 2,4-ditertiary butyl phenol and our confirmation compound, which is the tetrahydrofuran. What's also important, because plastics are so common, is to ensure that the entire process from filtration to analysis is plastic-free. And that's what we can see here. So we've looked for the 2,4-ditertiary butyl phenol again, and that quantitation compound is missing. So we can confirm via this blank that we're not getting plastic contamination as part of the analysis. Now, the next step was to look at the level of PET in different beverages, which can be quantitated using this quantitation compound. And they've got 4 different sample types here. There's 2 bottled waters from different brands, a carbonated bottled water, and also bottled cola. And we can see here that apart from one of the bottled water standards, PET has been detected at concentrations of micrograms per litre in each of these samples. So, with thermal desorption, we're able to analyze down to 0.2 micron diameter particles. So this isn't just the microplastics, it's also the nanoplastics, which are now emerging to be of interest as well. It's quite common for imaging techniques to be used for this type of analysis, but they can only measure down to 10 microns. The technique provides concentrations in micrograms per litre, so you can really see what mass of plastic is present in your sample. It's compatible with a wide range of plastics as well, and provides information not just on which plastic is present, but can also look at constituents and additive compounds. Now, this is important for source profiling, but it's not just water. So water, soil, sediments, biota, and air samples, which is why we're highlighting it today, can be profiled using this technique. And compared to other techniques, it's greatly simplified. We even have the benefit with thermal desorption of being able to recollect the sample, to archive it, or reanalyze under different conditions. And when we use recollection, we don't have to re-prepare the filtrates as well, saving labs time. Now, our final application is PFAS. Now, PFAS are the forever chemicals, and they're in the media a lot at the moment. But what exactly are they? So, PFAS stands for per and polyfluoroalkyl substances. They've been manufactured and used since the beginning of the 1940s, where they gained popularity for their resistance to heat and resistance to staining. Now, sadly, it's these very properties that make them a real challenge to manage in the environment. And they are still used in multiple sources that you'll have in your home and your office today. Now, PFAS is a very broad catch-all term for these compounds, but it includes PFOA and PFOS, which you can see highlighted here, Gen X, and many other chemicals. Of these, the PFOA and PFOS have been most studied due to their extensive use, and they have now been phased out, but they remain in the environment within organic matter and the human body. But with those larger PFAS compounds being phased out, we now have new PFAS compounds, and these new PFAS compounds are more volatile. So the theory in making them more volatile is that they should be easier to remove from the environment than their predecessors, but there's very little real data on them and their long-term effects on the environment and how it will affect us, essentially. Now, the difference in volatility, though, does pose an issue for the traditional PFAS measurement techniques, which focus around LCMS. So GCMS is now being assessed for these compounds, and especially when we're looking at them in air. Okay, now aqueous film-forming foams, or AFFFs, are used in firefighting, and in the past they contained PFOS and PFOA. They're particularly useful in managing fires with petrochemical sources and are used widely by government. Today, they now contain different, more volatile PFAS compound, which, as we discussed, are essentially unknowns from an environmental and toxicological point of view. Now, in a recent study between Marks International, Jacobs Labs, Vista Analytical Laboratory, and the University of Nevada, TD was assessed for the sampling analysis of PFAS from AFFFs. As the AFFF is applied, these PFAS compounds can be released into the air as well as being released into the soil and therefore the water as well. So understanding the release of PFAS from materials like this is really important. Now, thermal desorption for PFAS offers a number of benefits. It's got a really fast sampling time, a broad analyte range, and we can look at the very volatile compounds which are going to be of interest here. Now, these three advantages should benefit the study, detection, and understanding of these chemicals moving forward. And in the example chromatogram you can see here, this is the untargeted analysis of the AFFF foam, which has been carried out under controlled conditions. Now, the sample was taken over a 2-minute period, so very fast, immediately after the foam had been agitated in the reaction chamber. This short sampling time allows us to get a snapshot of what the foam is emitting immediately after application. And these set of test samples were also repeated an hour after to assess how the emissions into the air had changed during that time. Now, from this untargeted screen of the AFF, we can immediately pull out a number of PFAS compounds which have been highlighted here. And also we had a tentative identification of PFOA, which, whilst tentative, was of interest to us and our collaborators. Now, TD as a technique was able to quickly and easily sample the compounds, capture a wide volatility range, and importantly, capture the very volatile compounds which will be of interest in future. Now, that's the last of our applications. I hope we've shown today that the advances in TD technology helps to facilitate the analysis of wide compound ranges in a single analysis, making it ideal for complex target lists and untargeted discovery methods. Thermal desorption isn't just for airborne VOCs, we can also do direct desorption of filters. We have highly inert flow paths and gentle heating programs which make compatibility with reactive compounds like formaldehyde, as we've seen from air and materials, a possibility. And the low volume uniformly heated flow path provides quantitative analysis of SVOCs, such as the pHs we saw in our particulate analysis. This means that TD is really capable of taking you from discovery all the way through to routine. Now, thank you very much for your time. Lauren, do we have any time for questions?
Yes, we do. And thank you so much, Hannah. Great information in there. So without further ado, let's dive in. Just as a reminder, though, if you do have a question, feel free to type that into the questions module in the GoToWebinar control panel, and we will do our best to get to them. All right, let's dive in. First question. Have you observed carryover when loading canisters under vacuum on the CIA Advantage auto sampler when analyzing samples of varying concentrations?
That's a very specific question. I'll tell you what, because it's such a specific question, I'm going to say no for a start. The CIA Advantage is perfectly suited to handling a range of samples, whether they're vacuum or whether they're pressurized. But if you do want any more information, please let us know and we can get in touch and give you some more on that.
Fantastic. Next question is, what is the primary column for formaldehyde detection?
So the primary column, which was used to separate the C2 and the C3 compounds, but not the formaldehyde here, was a Illumina plot, I believe. The formaldehyde column itself, I would have to check what that is. So Lauren, if you can take down the note of the speaker, and we can get in touch and see if that's the column they're actually looking for.
Absolutely. And this actually might be a similar situation for this next question. Can you provide detailed column specifications for the FID MS analysis?
Yes, we can. I won't give them out here because we've got different configuration depending on your GC instrument as well. So Lauren, if you've got the details, we'll get in touch after the webinar.
Fantastic. Let's try this one. Why is recollection useful for air samples?
Now, recollection is useful for a couple of reasons. You can save your sample for a later date. So say if the sample is very valuable, you've gone to the Amazon rainforest, you've trekked all the way there, you've got bitten by mosquitoes, you've taken your sample and you get back to your lab. Now you only have one of this sample and you don't really know what's on it. So by using recollection, you can analyze your sample, but also make sure that you can keep it at the same time. So if you do need to go back and look at that sample again, you still have exactly the same sample as you started with.
Very interesting. All right. Next question is, what happens when products containing PFAS are disposed of?
Now that's a really topical question, actually. So PFAS products, well, products containing PFAS generally at the moment are incinerated. And when they're incinerated, there's concerns about whether the PFAS compounds are broken down and what compounds they're broken down into. Because the PFAS contain fluorine, there's a chance that when they break down, they can be converted into CFCs, which are greenhouse gases, which have a really long lifetime in the atmosphere. Now, the benefit of TD here is that you can actually monitor the CFCs and the PFAS compounds. So if you wanted to assess the breakdown of the PFAS compounds at disposal, you're able to do that with the same system.
Awesome. And I apologize if I got this question wrong, but can you quantitate recollected sample data?
You can. So recollection is quantitative. So as you inject your sample, say you have your sample concentration is 10 ppb, and you inject 1/10 of that into the GC system. When you recollect, you then have 90% of your sample left. So you know that you've got 9 ppb on your sorbent tube where you've recollected. So the next time you analyze it, you can take that into account. So you know at every time you recollect what amount of sample should be on your sorbent tube based on the initial sample concentration.
Fantastic. And I think this one might be the last one, but how do microplastics get into the air?
Yeah, so we don't usually think about microplastics as being in the air. Most of the content in media at the moment is focused on water, but what you'll actually find is there are a lot of plastics in the air. So one of the most common ways that plastics can be transferred into the air is through your clothing. So anytime that your clothing, you rub your clothing or there's any contact or friction, tiny bits of the plastic that make up the fibers can break off and then be released into the air. Same is true of carpets and other materials that contain plastics.
Very interesting. All right. That looks like it is. Um, oh, I've got one more question, and then we're going to call it. Then we'll call it done. If you load internal standard prior to splitting for recollection, um, will no adjustment be needed to account for the split?
Okay, just trying to think quickly on this
Yeah,
question.
and I
So
might be messing that question up.
can you just repeat the question quickly, Lauren? Otherwise, we'll have a look
Oh,
offline.
maybe this was actually more of a statement. If you load internal standard prior to splitting for recollection, no adjustment will be needed to account for the split.
Yeah, so if you load your internal standard prior to recollection, you will have your internal standard on your recollection tube as well. Um, so it works in the same way, essentially. You know how much internal standard you put on, you know how much internal standard then got injected into the GC, so you can then work out from that what concentration is left on your TD tube.
Fantastic. All right. So we are at the top of the hour. If we didn't get to your questions or if we needed to clarify, I have all your information and we are going to get you a personalized response. How great is that? Thank you so much, Hannah, for joining us today. And as a reminder to everybody, you're going to be receiving a link in the next day or two with a link to the recorded webinar. So you can watch this again and look back at some areas that you want to get some more information on. Of course, I'm going to encourage you all to visit lqa.com/resources for future webinar details and to access our library of recorded on-demand sessions. Well, that is it for us. Everyone, have a good rest of your day.